Because the velocity is larger, we get a lower pressure on the smaller side. You can see this effect if you're unlucky enough to be in a car where someone is smoking. If the window's down a little bit and you're on the interstate, the high-speed air outside the window will create lower pressure, and the higher pressure in the car will blow the smoke out the window. If the car comes to a stop, there's no reason for the smoke to move since the pressure will be the same on either side of the window. The main equation that we're going to use for fluid dynamics at this level is called Bernoulli's equation. And what this says is if we pick any 2 points in a pipe, the following is true. The pressure plus 1/2 density times velocity squared plus density times g times height is the same at both point 1 and point 2. This is pretty clearly a conservation equation, and we could ask ourselves what's being conserved here. If we multiplied by unit volume everywhere, say 1 cubic meter, the left side we'd have P1 times that volume plus 1/2 rho times that volume V1 squared plus rho times that volume GH1. But notice rho times the volume is just mass. So the two terms here at the end, 1/2 become 1/2 mv squared plus mgh, kinetic and potential energy. What about the P times V? Notice that we could write this as pressure times area times some other linear dimension like distance. Pressure times area is force, so this is force times distance. This is work done on the fluid. We don't have a non-conservative term here like we had when we were talking about work in general, since we had to include friction. We're not including friction since we've already ruled out viscosity. So this Bernoulli's equation is really just a restatement of the conservation of energy. And there are a few interesting problems we can solve here. One of them, let's say we have a large tank of water open to the air, so there's no top, and there's a tiny hole in its side. How fast does the water shoot out of this hole? So we're going to say the top of the water has a height h above the ground, the hole has a height y, it shoots out here to some distance x, and we call the top of the water point 1 and the hole in the side point 2. Notice that the pressure at both the top and the side, both places it's just atmospheric pressure since they're both open to the air. So P1 is P0 and P2 is P0. We can then get rid of the atmospheric pressure on both sides, and we get this. We've got the same density everywhere, so we can get rid of that. Now we're down to this, and we put in our heights. H1 is H, H2 is Y. We get this, and now we have to stop a minute. We have two unknowns. We don't know V1, we don't know V2, but we only have one equation. This problem is in practically every intro physics book, and there's two ways you can do it. What you commonly say is the area of the hole is negligible compared to the area of the top of the tank, so pinhole inside of a very large water tank. In that case, A1 is huge compared to A2, and that means by the continuity equation, V1 is tiny compared to V2. In other words, the velocity of the water spraying out is much, much higher than the velocity of the water level dropping. If you do that, once you square them, V1 squared is even smaller than V2 squared, so we can just set it equal to 0. We get rid of this term, and we can write that velocity of the water coming out the side is square root of 2g times h minus y, or the height difference. This is kind of what we would expect based on our earlier work with energies. To actually do this, we'd have to give you the area of the top and the side. So let's say the area of the top is 10 times the area of the hole, so it's not negligible anymore. Continuity equation then tells us that the velocity of the water level is dropping 1/10 as fast as the water shooting out of the side, and we plug those both in here without neglecting anything. And when we solve it this time, we get that V2 is pretty close to what we had before for this case, square root of 1.01 times what we would have gotten before. We can do one more example Bernoulli problem. Let's say we have a pipe that has a diameter of 0.9 meters at its low end and 0.18 meters at the high end. Let's say the low end is 0, like we usually do with potential energy problems, and the high end is 67 meters. If the high end is open to the atmosphere and it's spraying water out, and the lower end we have a velocity of the water of 2.4 meters per second, how fast is the water spraying out of the upper end? And a different question, what's the pressure at the lower end? So to find the speed at the upper end, we can just use the continuity equation. We say the lower end is 0.1, the upper end is 0.2. We find our areas. The continuity equation tells us V1 times A1 equals V2 times A2. So we get that V2 is 61.1 meters per second, which is pretty fast. At the bottom of the pipe, we can find the pressure by plugging in everything we know. We know the density of the fluid. We know the velocity at both top and bottom. We set the height at the bottom to be 0. We know the height at the top is 67 meters. And we know the pressure is just atmospheric at the top. So we solve this for P1 and we get 2.62 million pascals. This is about 26 atmospheres. This would take